One more example of constant acceleration. So I have a plane here, and let me define my I hat and J hat. So initial velocity is 5 meters per second. I hat, let's make this 4 meters per second I hat plus 3 meters per second J hat. And let's make the acceleration is a long line of velocity with acceleration, no vector symbol, equal to 3 meters. A long line of velocity and in the same direction. The 3 meters per second squared. What is the velocity after, let's just say 5 seconds? I'll make it 6 seconds. Recognize that I've expressed this as a two-dimensional problem here, but this is still a one-dimensional problem because this thing is traveling sort of in that direction right there. So I could work this out. This is along the same direction, so I could come up with a vector in that direction and then break this up. So we have 4, 3, and this is my velocity, and this is along the same line in the same direction, and so therefore they are proportional triangles. So that's 3, and I don't know what those are. And let's just go ahead and do it that way. This is the long way. There's a much shorter way. So Pythagorean theorem, so that would be 5 meters per second. And so 5 is the 3, as 4 is the something, as 3 is the something. And we'll pull up a handy dandy calculator. So this is 2.40. I could have, that's 1.8. And so my acceleration is 2.4 meters per second squared I hat plus 1.8 meters per second squared J hat. I have my initial velocity. So if you're going to solve it this way, we need to, in essence, treat this as two separate problems here. So I have my I hat and J hat, and then delta S, VI, VF, A, and T. And so I'm basically going to break it down. So this is 4 meters per second, and in the J hat direction, this is 3 meters per second. My acceleration is 2.4 meters per second squared and 1.8 meters per second squared, and 6 seconds. Time's the same regardless of which direction you're going in. And so I can treat this as two separate problems here. And so plugging into V is equal to VI plus AT. I end up with 4 plus 2.4 times 6. They're in the same direction. I made that positive. That's, of course, would be positive also. 18.4. This is for the I hat. And for the J hat, this becomes 3 plus 1.8 times 6, 13.8. And so the final velocity would be 18.4 meters per second I hat plus 13.8 meters per second J hat. That would be the answer given that coordinate system. Or, alternatively, I had this thing going 4 meters per second to the right, 3 meters per second up. It's a 3, 4, 5 triangle, so that's 5 meters per second. That would be a 37-degree angle, 36.8 something, I believe. More specifically, that angle right there is the arctan of 3/4. And let's just be retentive for the moment. 36.8698976458 degrees. And that is rounded off to the 10th decimal place. I'm just going to redefine my coordinate system. I'm now going to define my coordinate system as I hat in that direction. Or actually, I'm just going to make that the positive direction at that angle theta there. And so now the problem becomes I have delta S, VI, VF, A, and T. So acceleration is in the same direction at 3 meters per second squared. My velocity is 5 meters per second squared time is 6 seconds, and I'm trying to find this. And so my V final is equal to 5 plus 3 times 6, or 5 plus 18, or 23 meters per second in the positive direction, because I said that was the positive direction. So it's a two-dimensional problem, but I can change it into a one-dimensional problem just by changing my coordinate system. Now, is this the same answer as we had before? Well, this would be the magnitude of that vector there. So I have 18.4 to the right and 13.8 up. So the magnitude here, let's do a little Pythagorean theorem. So 18.4 squared. So 338.56, 13.8 squared, 190.44. Add them together, I get 529, and then the square root of 529 is 23 meters per second. How about that? And I did this for a different video. However, I'm going to throw this in here. Yeah, don't forget that.